here we have breakout example problem time. So let's put to test what it is we have learned up until this point. This is the type of example problem that I would again encourage you to pause the video, see if you can't solve it for yourself. Spoiler, this problem does have a little bit of a trick to it, so as you are attempting it, keep in mind that it may seem like you are missing a necessary piece of information, but you can actually find it. So be thinking a little bit outside of the box, think creatively. Silver has two known stable isotopes, silver 107 and silver 109. If the average atomic mass that you can find on the periodic table for silver is 107.9 atomic mass units, and silver 107 has an isotopic mass of 106.9 atomic mass units with a natural abundance of 51.89%, what's your isotopic mass of silver 109? All right, so again, take a brief moment, take a pause in the video, break out the calculator, see if you can't solve this problem for yourself. All right, unpausing the video, then welcome back. I always say this assuming that everyone pauses, and I hope that you do, right? Science is, particularly learning science, is an interactive process. You can't just sit here and absorb everything I'm saying and hope to be able to do this type of problem for yourself. So again, emphasizing, if you haven't already, please try this problem yourself. If you did, great job. Let's see what the answer is. All right, so let's gather everything that we know. Again, there's no shame in just gathering the information first. You have to know what you're working with. So we know that silver has two known stable isotopes. There are only two of them, silver 107, silver 109. So we know also on the periodic table that silver has an average mass of 107.9 atomic mass units. So what this tells us, just to go backwards and observe our equation, in fact, I'll just clean this slide off. We know what silver's average atomic mass is. We've been told that this is 107.9 AMU. So it looks like we're actually going to be finding one of the fractional pieces of information. And as we continue to read, that is exactly what we are asked to find. We are looking for the isotopic mass of silver 109. All right, so let's continue gathering things that we know though. So we are told that silver 107 has an isotopic mass of 106.9 AMU, and it has a percent abundance of 51.89%. Silver 109 is our big old question mark in terms of mass, question mark AMU. Right, in math they teach you always use variable X, or that's the variable that's used the most commonly. I just honestly love throwing in question marks. I want to make it explicitly clear, what are we looking for? So this question mark is going to represent our unknown variable. This is what we're trying to find. Well, in order to solve the problem, we need an additional percent, right? According to our equation, if we are given an isotopic mass, we also need to know how much of that is there in the world in order to figure out what the average is. So it would appear as though we actually have two unknowns in this problem. But again, I did say there was a little bit of a twist. So we are told in the wording of the problem that there are two known stable isotopes. Again, 107 and 109, and that's it. Which means if silver 107 is 51.89% of all of the known silver, silver 109 has to be 100% minus how much we know of silver 107 exists. So 100 minus 51.89%. Right, again, two stable known isotopes. Between the two of the known isotopes, the total abundance has to sum to 100% because that's all there is. So if it appears as though we are missing a percentage, but we also know how many known stable isotopes there are, we can make a little bit of an assumption, and this is a totally valid assumption to make. So it turns out that the total percentage of the silver 109 ends up being equal to 48.11%. And so here now we have every piece of information we need to actually set up and solve the problem. We know, quote unquote, what the answer is, we know what the average is, and we now know what the, what both of the percent abundances are. We're given one of the isotopic masses. All we need to do is insert all of our information to our previous equation and solve for the question mark. All right, so let's go backwards and actually do that. We have two isotopes. The first, we know, has the isotopic mass of 106.9 AMU. And that particular isotope comprises 51.89%, or in fractional form, 0.5189. Right, so this is near, or like just over half of all of the silver that exists, and the particular isotope that this represents is our silver 107. All right, we're gonna add this to our question mark in atomic mass units. Again, this is what we're looking for, so why not just make it explicitly clear this is a question mark? And the fractional abundance of the isotope that we don't know its mass, again, is 48.11%, which is equal to 0.4811. This component of the total sum of that weighted average, again, represents silver 109. All right, so algebraically, all we need to do is rearrange and solve for our question mark. So in order to do this, first, we're going to combine pieces, subtract it to the other side. So honestly, what I'm just gonna do is represent that we are going to take our 106.9 AMU times the 51.89%. We're just gonna subtract this whole piece, 106.9 AMU times 0.5189 to the other side. So we're just gonna subtract this to the other side. And then we have to divide each side by the fraction that is presented here, the 0.4811. Divide on the left-hand side by 0.4811. All right, so yeah, I'm making kind of like hand-wavy math here, but we subtract the silver 107 to the other side first, and then we divide by our fractional abundance. When we do so, what we're gonna find is our question mark is actually equal to 109.0 atomic mass units. All right, so we know now what the isotopic mass of our silver 107 is and the isotopic mass of our silver 109. Coincidentally, here we can see 109.0, where again, the mass number is approximately equal to what the actual isotopic mass is. So it makes sense. That's actually a really good way to be able to check your work. Make sure that your mass number is approximately, if not actually equal, to your isotopic mass. If it's not, there are a couple of places where the algebra could have gone wrong, right? If you're not following algebraic order of operations, your answer is going to end up off. Or if you don't actually convert your percent abundances into fractional abundances, again, your answer is going to end up being off, possibly even by up to a magnitude of like 100. So double check your algebra, make sure you're inserting fractional abundances, and if your math came out correctly, you should have an answer of 109.0 atomic mass units.